Hello, and welcome everybody. If you're watching this video, you've missed day 2 of our week 3 Computer Science Principles class, and you're watching this to catch up. What we've got going on is we are moving on from just basic binary to talking about some issues or potential issues that could arise when you use such a system. So we're going to look at overflow, underflow, and round-off errors. We're going to do a Jeopardy game, which you guys will have to check out on your own. And we didn't quite get to representing text today, so we will be covering that first thing next week. Let's get started. So for our warm-up, I asked a very simple question. If I gave you 9 $10 bills, 9 $1 bills, and 9 dimes, what's the largest amount of change you could give somebody? Well, that would be $99.90. Very easy question, right? What's the smallest amount? 10 cents. But what happens if we have to give 7 cents of change? Well, that's hard to do. We only have 10 cents, right? So we could give them 10 cents and say, oh, well, keep the change. We could ask for 3 pennies back, but they probably wouldn't have it. So it puts us in a really awkward spot as a cashier, right? What we're going to see later in the lecture is we can be in that awkward spot as a computer. And being in that awkward spot often leads to some really disastrous consequences. One thing that we'd like to start off with here is this activity or widget that you can check out by either clicking this link or navigating to code.org and clicking on the second bubble under lesson 5 in our class. So what this is an odometer, much like the one in your car, but this one counts in different bases. You have one for binary, octal, decimal, hexadecimal, and you can even put your own base, whatever you want in here. So let's go ahead and give it a start and see how it goes. Notice that the binary, of course, will count up faster. Now, what I mean by that is the numbers are obviously equal to each other. These represent the same number. In this case, this decimal is probably the easiest one for us to understand. But the binary digits, we need a whole lot more places for really, really fast than the other ones, right? Because each place value is only holding a power of 2, whereas here each place value is holding much larger numbers, since they're powers of 8 or powers of 10 or 16. So then what happens if we were to count up to all the way as far as we could get to in binary right here? What if we tried to go past this amount? Well, as you just saw a second ago, it gives us an overflow message. What does that mean? That means we tried to flip this next bit, but the computer wasn't expecting us to have a bit there, so it didn't do that. What it did instead was it just flipped all of these to zeros, as it normally would, and kept going. Essentially, your huge number that used to be stored in here suddenly became 0. Well, that's the opposite of what is good. That is a horrible situation if that number is a part of an important calculation. And in fact, there have been spaceflight issues that have resulted from this kind of error. There have been bank issues. So this is a fairly common and well-known pitfall for computers. How do we get around this? Well, you have to be clever as a programmer. You have to either anticipate how much information you intend to store and tell the computer to set that many bits aside. Or you have to build in fail-safes where if this does happen, this isn't going to result in any kind of dangerous outcome. So that is what an overflow error looks like. Let's go back and keep going here, and we're going to take a look at an underflow. Actually, we're not going to look at an underflow, but you can imagine that if we were going the other way and we went past all the zeros, we'd loop back around to the largest number we could get, which would also be equally terrible. The next thing we're going to look at is going to be round-off error instead. So round-off error really has to do with the way binary represents decimals. And by decimals, I mean not the decimal system, but literal numbers smaller than 1. So fractions, so half, a quarter, and so on and so forth. In the binary system, we will be using 2 to negative powers to create our decimal points, right? Or our place values past the decimal point. So in decimal, if you think about it, our tenths place is actually 10 to the negative 1, just to the right of 0, right? And if we go to the second decimal spot, well, that's just hundredths, or 10 to the negative 2. Well, it just so happens it works the same way in any number system, but it's much, much harder to make various decimals we take for granted, various fractions or parts of a whole, because of how difficult it is to be precise in these systems. So take a look at this. You can take a regular flippy-do, and you can decide to use a part of it for numbers smaller than 1, so fractions. So in this case, we use 2 of the last spots to represent 2 to the negative 1 and negative 2. You could have done the same thing, but started at negative 3 or negative 4, and you'd have a flippy-do that's able to do some kinds of fractions. In this case, this is very limited. Think about it. What can we represent here? Well, we can only really represent things that are quarters. 0.25, 0.5, 0.75. We're really out of luck if we try to represent something like 39 cents, right? There's no way to get 0.39 with just those 2 decimal spots. We can do it in our system, in the decimal system, since those decimal spots, I can't get away from saying it that way because it's the most intuitive, but really in binary, that's not what they are. Those decimal spots actually do represent decimal numbers, powers of 10. And so if we wanted to represent something like, let's say, 0.17, that's fairly trivial. We just need 2 places to do that. But let's see if we wanted to represent the same thing in binary. Well, we could go to Google here, and we could simply type in decimal to binary fraction calculator. And that'll give us this beautiful machine right here, which you guys are welcome to use. Let's go from decimal to binary, and I'm going to put in 0.17. How many places are we going to need? Well, here we had 2. Are we going to need 3, 4? No, we're going to need this many. Oh my goodness, that's so many or in this case, binary slots, right? So many powers of 2 to be able to be precise enough to represent 0.17. So it gets really, really large really fast, and it might not be economical for your system to devote that many bits to storing fractions. Oftentimes, it makes a lot more sense just to round. In fact, if we were to round here, we would maybe just round this to 0.5 if we were just using the 2 spaces for storing fractions, as in the example. So it becomes trickier and trickier the smaller your number is to store it precisely. Let's keep going. So the following activity we did in class, we estimated how much of this total circle this piece of pie would be. This piece of pie would be this one and this one. And then we tried to figure out how we would represent that in binary. And it turned out it was very, very difficult to get close. And we ended up with more pi in our calculation than the actual pi present, farther enforcing the fact that it's really difficult to represent fractions in binary. So that is a limitation it has, and you have to be very careful with that. For instance, if you're doing banking transactions, you want to make sure you're not accidentally leaving some money behind for the computer to just gobble up. That would be rather catastrophic if even fractions of a penny were left over every time we did a transaction. Over time, that would be a lot of money. All right, so to recap, overflow error is when we go too far in our numbers. Round-off error is what happens when we can't represent a number precisely enough because we do not have enough bits to do so. The last thing we did is we practiced some conversions using this Jeopardy game here. You guys can access this through the PowerPoint slide by clicking on the link. You can select No Team, and you will get this screen. These are some problems, and they're divided into various categories. You can explore these on your own. I hope you do. And we will be continuing with talking about text and how to represent it next time. Please don't forget that 0.04, 0.02, the conversion assignment, is due Friday at midnight. So do not forget to turn that in, please, so I can give you full credit and you can have an A in my class. I hope you have a great rest of your day, and I'll see you later.